Hello, I'm Amar Zaman. In this talk, I'll present depth perception cues in VR under sleep deprivation, where we compare explicit and subtle depth cues and evaluate their robustness under overnight fatigue.
This work builds on our prior idea of subtle augmentation. The goal is to communicate important information in VR without cluttering the scene or hiding the visual evidence users need. Imagine an industrial inspection or teleoperations setting like this. Users have to integrate multiple information sources, operational status, material condition, and visual details like surface texture. Often, the critical evidence is in the image itself, for example, rust or small surface defects. Traditional augmentations like text overlays or color coding can help, but they also risk occluding texture, adding visual clutter, and increasing cognitive load, especially when objects are dynamic or when the user must split attention across the scene. That motivates the key design question. Can we convey information in a way that remains legible and stable without demanding constant interpretation? For this paper, we focus on one concrete information channel, depth, because it's fundamental to interaction, and it can be supported in both explicit ways, text, color, and subtle ways, blur. The rest of the talk asks, under fatigue, which cue strategies remain robust?
Why do we care? 1. VR is now used in extended high-stakes contexts like training, monitoring, and teleoperation where fatigue is hard to avoid. 2. Sleep loss doesn't only slow people down, it destabilizes wakefulness, causing intermittent lapses and missed responses. 3. VR lets us augment the scene with depth cues, but the open question is, which cues remain robust when users are sleepy? 4. So we frame this as a design trade-off, improving accuracy while preserving responsiveness, avoiding missed responses. RQ1 asks whether fatigue interacts with cue type to change both response probability and depth error, so we can capture the accuracy-responsiveness trade-off. We hypothesize blur is more robust to fatigue-related drops in responding than symbolic cues. RQ2 asks whether cues keep their accuracy advantage over baseline across sessions and distances. We expect all augmented cues to help. RQ3 asks whether explicit overlays increase perceived effort or sickness compared to blur under fatigue. The contributions are an overnight within-subject comparison of explicit versus subtle cues, a modeling approach that separates lapses from accuracy, and concrete guidance for adaptive cueing under low alertness.
Participants perform a VR asteroid depth judgment task. The target starts at 10 meters and moves toward the user. A catching frame defines the correct depth plane at 3, 5, or 7 meters. The participant presses the trigger at the moment they believe the asteroid reaches that plane. We compare 4 cue conditions on the asteroid. No cue as the baseline, text, which explicitly shows metric distance, color, which encodes depth via a near-far color mapping, and blur, a subtle depth-dependent texture blur that increases with distance. Importantly, we treat 2 outcomes as primary. First, response probability, whether the participant responds at all, capturing fatigue-related lapses. Second, on the trials where they do respond, we compute squared depth error to quantify accuracy. For responded trials, we compute signed depth error, early versus late, but analyze squared depth error as the primary accuracy metric. We use squared error to model error magnitude, so early and late responses don't cancel out when averaging, and because it penalizes large misses more, matching the task's operational motivation. This sets up the core question. Under increasing fatigue, which cue improves depth accuracy without increasing missed responses? This is our controlled 27-hour sleep deprivation protocol.
Participants complete 6 sessions across the night, from 20 through 07. We capture performance across increasing fatigue and the circadian trough. Each session takes about 37 to 40 minutes and follows the same structure. We start with a 3-minute PVT as an objective vigilance check. Then we collect pre-task ratings, including KSS sleepiness and mental effort. Next is the VR task. Participants complete 4 Q blocks, each with 81 trials, so 324 trials per session. After each Q block, we collect KSS, effort, and SSQ, so we can track both performance and subjective state over time. This is a within-subject design with counterbalanced Q order using a Latin square. We also tightly control the environment: no caffeine, fixed meals, constant lighting and noise, and continuous monitoring to ensure the manipulation is real and consistent. The study runs on a Quest Pro at 72 Hz with a Unity implementation and a minimal scene to avoid extra depth anchors.
Before looking at Q effects, we verify the fatigue manipulation worked. On the left is objective vigilance from the PVT, summarized as mean reciprocal reaction time. We see a clear decline across the night, with the lowest vigilance around 05 to 07, consistent with the circadian trough and sustained wakefulness. On the right is subjective sleepiness using KSS. Sleepiness rises across sessions, peaks around 05, and then slightly improves at 07. Importantly, the KSS by condition is essentially flat. Q-type does not change how sleepy participants report feeling. That's useful because it means Q differences later reflect performance under fatigue, not differences in fatigue itself. Both measures show strong session effects, confirming the manipulation. Result 1 is responsiveness, measured as the probability of responding on a trial, essentially 1 minus lapse rate. We analyze this with a binomial mixed effects model because response is binary, respond versus no response. In the early sessions, responding is near ceiling for all Qs. The key pattern is the divergence at 5 a.m., which aligns with the circadian trough. At that point, text shows the lowest response probability, while blur and color maintain higher responsiveness. This is important because it suggests that under peak fatigue, explicit symbolic cues may increase lapses even if they later help accuracy. So this sets up the core accuracy versus responsiveness trade-off we'll see in the next result. To quantify the trough effect, at 5 a.m., the odds of responding are 4 times higher in no Q than text, and blur and color are also significantly higher than text. So the lapse risk penalty is concentrated at peak fatigue. Text hurts responsiveness most at 5 a.m. relative to others.
Result 2 is accuracy on responded trials, measured as squared depth error, so lower is better and large misses are penalized more. We analyze squared depth error with a gamma mixed effects model with a log link because the errors are positive and right skewed, and we model Q, session, and distance with their interaction. In the plots, you see 2 strong main patterns. Errors increase as fatigue progresses through the night, and they also increase with distance. 7 meters is clearly the hardest condition. Across all distances and sessions, all augmented Qs tend to reduce error relative to no Q, but text is the most consistently accurate across the board, especially in the harder conditions late at night and for farther targets.
This summary makes the consistency clear. Text improves accuracy in every session by distance cell, while blur and color help in subsets. In a hard late-night FAR case 07 at 7 meters, text reduces error to about 0.34 times baseline, compared to 0.65 times for color and 0.77 times for blur. Text improves accuracy most in a demanding case, relative to baseline, ratios. Finally, RQ3 asks whether explicit overlays increase subjective burden. The short answer is no Q-specific burden effect. Effort and SSQ change across the night, consistent with fatigue, but they do not differ meaningfully by Q. So the performance differences we saw are primarily fatigue-related, rather than driven by Q-induced discomfort.
This synthesis combines the 2 core outcomes, responsiveness, response probability, and accuracy, square depth error on responded trials. So putting RQ1 and RQ2 together, text is the most accurate, but it can carry a responsiveness cost at peak fatigue, which motivates fatigue-sensitive queuing. Qualitatively, text sits furthest right. It produces the strongest and most consistent accuracy gains, especially in hard late-night far-distance cases. But around the circadian trough, 05 a.m., text shows the biggest dip in response probability, while blur and color preserve responding better. Design implication: be fatigue-sensitive, default subtle support, and escalate explicit metric overlays only when precision is needed, decision points, or on demand.
Based on these results, the main implication is that queuing in VR should be fatigue-sensitive, not one-size-fits-all. A practical policy is default to subtle depth support, like blur, because it tends to preserve responsiveness when alertness is low. Then escalate to explicit overlays, like text, only when you truly need metric precision at decision-critical moments, on demand, or when a system detects uncertainty or prolonged gaze. The second implication is methodological. Under fatigue, missed responses are a primary risk. If we only analyze completed trials, we can overestimate performance. So evaluation should always separate responding at all from accuracy when responding. In terms of limitations, we didn't have eye tracking, so underlying oculomotor mechanisms are inferred rather than measured, and the scene was minimal compared to real operations with clutter. A natural next step is to test adaptive queue switching using real-time fatigue proxies.
Thank you for listening. I'm happy to take any questions.